Hello IB, we're now going to move on with the second part of 17A. I just put this slide up because I just wanted to remind you that when we're starting with the displacement function, S is a function of t, when we differentiate that we end up with S dash of t, or our velocity function. And another way of writing that, which I didn't have last time, was doing it ds dt. That's that other notation like dy dx. So in this case it's ds dt. Differentiate that again, we have d2s dt squared. So another way of seeing that either as s double dash or a of t. So s double dash of t is the same as the acceleration. S dash of t is the same as your velocity. All right, so let's move on to here. In the textbook, it just starts off with this summary. So if we want to talk initial conditions, then we're talking when t is equal to 0 in our example, when we're starting off with the point wherever it might be and whatever it's doing. So we could talk about its initial displacement, its initial velocity, and its initial acceleration. So remember on your graph, if you're plotting this and you've got some equation for a function, don't ever include the negative part if we're only talking t is equal to 0. Remember your domain. Only ever plot what is in your domain. So when our displacement is equal to 0, so in that case, I'll do it with blue. Here we have a position where the displacement is 0, so it's at the origin. So according to this graph, if our value for displacement, s of t, is greater than 0, I'll do that in red, that's all this region here. So the point started to the right of the origin, and these are all positive values. So all of this is positive. So all through here, all of these are positive. If they're negative, that means they're to the left. So at this point, the point travelled in a positive direction, turned around, came back through the origin, and now went into the negative region down here. Remember, if you want to do your motion graph, it's basically looking along this y-axis. What happens along here, or the displacement axis? So your motion graph, you can imagine you're sort of standing and just looking from this perspective, looking at it that way. The point is going up, hits a maximum displacement, turns around, comes back down through the origin and down to the negative. So it's like imagining all of this is squashed over onto this axis. Let's now think about the velocity. Velocity, remember, is the derivative of our displacement function, s dash of t. So we're talking about the tangents to our graph. So in this case, if the tangent is 0, so the velocity is 0, pick a colour, let's go red. In this case, whereabouts is it red?
Give me a moment.
So we come across here, and that should line up nicely. That's the maximum there. So that's where our velocity is equal to 0. The slope of the tangent is 0. Whereabouts have we got it with if it's positive velocity? That we'll do that one in green. So that means the particle's moving to the right. Here's the positive slope. So it's moving in a positive direction away from the origin. And if it's moving to the left, it means it's moving in a negative direction. So we've got a negative gradient. So here we have the tangent of all these is negative. So it's moving in the left direction. So imagine this way, if we looked at it sideways, is to the left. And going that direction is like moving it to the right. So that's what the point's doing to the right. Stops, instantaneous velocity is 0. turns around, goes back to the left. So all this region here, negative velocity, moving to the left. Down here, we want to do our acceleration. So again, recall our acceleration is the same as the derivative of our velocity function, or the second derivative of our displacement function. So let's say we had a velocity function. I'm just going to draw some random velocity function, and I'm going to do it so we can do something like this, and then I'm going to go straight across. Oh, that's meant to be straight for the sake of this example. So if we have a positive velocity, then, if we have a positive acceleration, in each case we're talking about the gradient on the velocity graph. So here it has a positive gradient of the tangent, so that means the velocity is getting higher, which is what the axis says. The velocity is increasing. Then it's decreasing here, wherever it has a negative slope on a tangent. That's meant to be a nice straight line, so that's a negative. Velocity is going down. Remember, a decreasing velocity, if it's negative, it means it's getting slower and slower, but it's still positive. So it's still moving to the right, but it's not moving as fast to the right. This last one here is when the velocity is a maximum or a minimum. Okay, and down here I've tried to draw it straight, so we could have a constant velocity. So here it's constant velocity, which means no acceleration, or in this case it's a maximum, or it could have been a minimum. So that's when we have zero acceleration. Let's chat about a couple of these things. This is a table that's helpful for summarizing things. If we have initial conditions, it means that t is 0, which we've just talked about. If s is 0, it means we're at the origin. If v is 0, so if we have no velocity, then that has happened. If we flip back here, we've got 3 scenarios. The point is actually stationary. So here we want the gradient. Remember, it's the gradient of this line. So that's the only place where it's 0, where it's doing a turnaround. Here, there's no examples of where it's actually stopping. It's still always moving. It hasn't cut that axis here. So we've either got it stationary or it's stopping and turning around. So if it's reversing, it's either hit a maximum. So these two are sort of related. So if it's hit a maximum displacement in the positive direction and it's turning around, or it's hit a minimum displacement, so it and turning around. So those two are related. It's stationary. Remember, we can have stationary points. When is a point, when do we talk about stationary points? So stationary points, we'll remember when f dash x is equal to 0. And that can happen at, in this case, a maximum, a minimum, or that horizontal point of inflection. Squeeze that in, horizontal point of inflection. So where we get an instantaneous inflection. It's an instantaneous stationary point. It's an instantaneous stop. So 3 options to that. 2, 3 options. Okay, so when a particle reverses, changes direction, its velocity must change sign. That makes sense. Corresponds to a local maximum or minimum. Remember, it's only a local. It's not necessarily a global. When do we have 0 acceleration? 0 acceleration happens when we have that horizontal tangent on our velocity graph, and that's what we were looking at over here. 2 scenarios. Either we've got the constant velocity, and so our tangent is horizontal, or we've hit a maximum in the velocity, or a minimum. We could have had this dipping down and had a minimum. So 3 scenarios, a maximum or minimum velocity, so that's those two, or a constant velocity, gives us 0 acceleration. So don't forget to stop and take notes of things and write down any questions. All right, let's now have a closer look at speed. Remember, speed is just how fast something is going at any instant. It's just the magnitude of the velocity. Remember, it's a scalar. There's no direction. The notation they've got here is with a capital S as a function of t. Be really careful you don't get these confused. The little s they've used earlier has been for displacement. If we jump back to here, see this small s, little s for displacement, whereas down here they're using a capital S as a function of time, because it still will be a function of time. It's just the absolute value of the velocity. So you won't often see it written like that in your IB, and I'll be careful at using that notation. Be very clear whether you're talking velocity and speed. Remember, you can put the absolute value of velocity into your GDC using the absolute value signs, and we'll practice that in class. So let's have a look at this. Here's your velocity function. I've just made up one that dips above and below, so we get a positive velocity. So all this time, the particle is moving to the right. It's moving in the right direction. Here, it hits a 0 velocity, so it's stopping, and now it's moving to the left because it's got a negative velocity. So in terms of a motion graph, it would be moving this way, and then stopping, and then turning around and moving back. All right, let me just draw that. So it's moving to the right, and then it stops, and then turns around and starts moving back. So it gets faster moving back, and then slows down, stops as if it's about to turn around again. All right. So if we want to do the speed, in other words, we want the absolute value of the velocity, then whatever is positive stays positive. All right, and that's what we've talked about here. If the velocity is positive, it just stays the same. So that part stays the same in the graph. If the velocity was negative, then we want to change the sign of it. Remember, if it's 0, it's considered there. So in other words, this graph then becomes this, if I can copy it like there. So that's what our speed graph looks like. It's the same, comes down, and now just keeps coming up again. So it's always positive. We don't have this negative part when we're talking speed. So if the signs of velocity, let's go through these now. If the signs of the velocity function and acceleration are both positive. All right, what's acceleration? Remember, it's the derivative of our velocity. So if the velocity is positive, here it's positive, our acceleration is positive. Let's go red, so we want there. What's the gradient? Positive. Velocity positive, gradient positive, then the speed of the particle is increasing. And we see down here, it is increasing. It's getting faster and faster. All right. So the other option is that they're both positive or both negative. So here we now have negative velocity. Where's the negative tangent? That's here. So there's a negative tangent. So we've got a negative acceleration and a negative velocity. So they're both matching. And if we come down to our speed graph, here we see the speed's getting faster, faster. Those are the two regions where the velocity is positive and the acceleration is positive, or the velocity is negative and the acceleration is negative. Both cases, the particle's getting faster and faster. In this example, we've got the signs are opposite. So we've got a positive velocity and a negative. So that's positive and that's negative. Whereas in this one, let's just put that sort of in here, positive, positive, or negative, negative. So coming back here, positive velocity, this region. Negative acceleration means a negative tangent. Where does that happen? All this region here. Nice straight line, not. Or we could have had negative velocity and positive acceleration. Here's our negative velocity, here's our positive acceleration. In both these cases, the particle is getting slower. So down here we can see on our speed graph that the particle is getting slower and slower in its speed. So that's this region, all right? And in this region, it's getting slower and slower. So a lot of these you do need to think through very carefully and slowly to make sure you interpret it correctly. So have a look through that. This is very similar to what we've just talked about, where the positive velocity, all right, then if it's positive velocity, then our speed is the same, all right, and so the acceleration, if the acceleration is positive, which is what we had in this case, that means ds dt is positive, so the change in the speed is positive, implies the speed's increasing. So all of that, oops, I'll go red, sorry. That's just talking about that first scenario where we've got positive velocity, positive acceleration. That's matching that one. Whereas here, negative velocity, negative acceleration of those two negatives, which was that region down here. So up here is case 1, and down here was case 2. All right, negative velocity, negative acceleration. All right. Okay, let's move on here. Let's do a couple of examples. We've got this scaffold for us. So here's our displacement function, t squared minus 5t plus 4. Displacement graph against time. First job, what you always do is what? That's right, factorize it, and we come up with t minus 4, t minus 1. So that means we've got a graph, and I can look and see concave up with cutting through at 4 and 1, and the y-intercept is at 4. So if I can draw this carefully, we want to come down through here. We're going to touch down there. This is sort of looking reasonable. Okay, and we're going to stop here. We always want t greater than equal to 0. So what happens? So what happens between 0 and 2.5? So basically I've worked out that this is 1, that's 4. Remember your quadratics, your minimum in this case occurs at the midpoint of your two x-intercepts, which is at 2.5. And that point there, if we do the calculations, comes out at 2.5 for the x and minus 2.25 for the y value for the displacement. So we're going to come down and do a motion graph in a moment. Between 0 and 2.5, what's the point doing? It's moving, it's becoming more and more in the negative direction, so it's moving to the left. To the left. What's happening at time 2.5? It's got a horizontal tangent, which means the velocity is 0. It's stopping and turning. And then what's happening after that? The displacement is getting more and more positive, which means it's moving to the right. It's got a positive velocity. All right, the gradient in all this region here is positive, so it's moving to the right. So I'm just working through this quite quickly. If you wanted to come up and graph this properly, you obviously want to do it at these different times. It's got a bit out of the way. So At s equal to 0, that's our y-intercept. So we know that that was at 4. So initially the point is at 4. At time 1, it's at 0. So it's back at the origin. At time 2.5, we found out here, I did the calculation at another time, and it comes out at minus 2.25, which is this point here. And at time 4, it's now, as you can see on the graph, and from factorising, we're back at the origin. So basically, our point is starting here, it's going to the left, there, stop, turn around, and it comes back to there. That's where we've got, and it keeps going. We can keep that going with an arrow. So that's the motion diagram. So again, remember I talked earlier about considering your y-axis. Imagine all of that was squashed back onto this y-axis. So the point starting here, it's going down or to the negative, stops there, turns around, comes up, and keeps going. So that's, imagine all of that squashed over there in just moving along that one line. Sorry, these are long videos, but there's just a lot of detail, and I just wanted to be thorough, given you want to be able to keep referring to this. All right, so let's look at 7A2, exercise 1. Let's do question 1 together. So we've got an object moving in a straight line. Its position is given by s of t, t squared minus 4t plus 3. And yes, you're already thinking, I need to factorise it. So we've got t minus 3, t minus 1. Note we're coping with all of this without a calculator so far. Obviously, if you can't factorise it, then you're going to be using probably in a paper 2 with a calculator. We want to find expressions for the object's velocity and acceleration and draw sign diagrams. So we want our velocity function is, of course, our first derivative of our displacement function, which is 2t minus 4. Then our acceleration function is our second derivative of the displacement function. There's our first derivative, so we've differentiated it to go 2. All right, if we want to do the sign diagram, that's a linear equation, 2t minus 4, and the y-intercept is, the x-intercept is going to be where this is equal to 0. So if you do a quick calculation, we want where does 0, 2t minus 4, where do we have 0 velocity for our sign diagram? Comes out with t is equal to 2. So that means this point here must be at 2. It's a positive gradient, y equals mx plus b. So that means it's going upwards, rising up. So that must mean this side is positive, that side is negative, because that's our 0 at 2. So our particle has a negative velocity, then it has 0, it's stopping and turning around, then it has a positive velocity. Remember, negative velocity means it's moving to the left. So it's moving to the left, stopping, turning around, moving to the right. Here, what's the sign on our second derivative? It's plus 2, which means it's always positive. And if you think about this here, for t squared, it's a positive here in front, which means that's positive, which means our graph is concave up. So don't forget all your old rules on quadratics. So concave up, second derivative is positive. So our sign diagram's nice and simple. Next thing, find the initial conditions and explain what's happening to the object at that instant. So if we want to do that, when s of 0, what's the displacement when t is 0? If we substitute that back into our equation, we've got t squared minus 4t plus 3. So we've got 0 squared minus 4 lots of 0 plus 3 equals 3. Put 0 into here, and we've got 2 times 0 for the velocity, minus 4 equals minus 4. And our second derivative is 2. All right, so what does that tell us? So if our s of 0 at time 0, the displacement is 3, that means it's initially at 3 units to the right. To the right. Can I just go R? If our velocity is minus 4, okay, now if we go back to here, we see we've actually got a sort of a story. We've got seconds and we have centimeters. So we could actually say this is not 3 units. We could actually write this as 3 centimeters. Our velocity here is, let's write that here. If it's 4, it means it's moving at 4 centimeters per second. If it's negative, it's moving to the left. So it's moving left at 4 centimeters per second. All right, this is getting harder. What's our 2 mean? All right, so remember that we could interpret that as speed, but it means that this means our velocity is becoming more positive. All right, that's what a positive second derivative means. It means our velocity function is increasing. Okay, remember, if this is our velocity time, and if we've got a positive gradient, it's going like this. So our velocity is getting more positive. But because it was already negative to start with, let's draw it down here. Okay, it was a negative velocity to start with, and it's getting more positive. Okay, so this is meaning our the point, the velocity is getting more positive. Okay, now what's happening to the speed? Look at your graph here. Your velocity is -4, all right, that's what we saw it here. It's going -4, -3, -2, -1, 0. That's where the particle stops. So our particle is, if we do our motion diagram, it's at 3 centimeters to the right. So there's 0, here's our 3. So it's starting here, and it's moving left. So it's moving left. We don't know, haven't got a time for a crossing here, but then we know that if it's got a positive, eventually it's going to have a 0 velocity, which means it's going to stop, turn around and come back. I haven't plotted to see where that's happening yet, but that's what's basically happening. So at this point, initially, it's starting off at -4, the speed is decreasing. And that comes back to this earlier page here, if they have opposite signs. So negative velocity, positive acceleration, then the speed is decreasing. Try not just rote learn this, go for understanding. And if you ever just need like sketch a graph, then just sketch it to help you understand it. All right, so we've done answered A and B with A. Okay, let's look at C. In C, it says describe the motion at time t equal 2 seconds. At time equal to 2, then we've got 2 squared minus 4 times 2 plus 3. So we've got 2 squared is 4 minus 8 is minus 4 plus 3. What have I got? 4 minus 4 plus 3, and we come up with minus 1. Is that right? Minus 8 plus 5 minus 1. All right. And then its velocity at time 2, remember, was 2t minus 4. So we want 2t minus 4 equals 0. All right, so what's happening here? So that must mean that our point is now stationary. Stationary. So it's turning around. This is really messy writing. Let me write this again so it's legible. So it's turning around. All right, it's hit a minimum, all right, because we've got a positive, just positive value for the t squared. So it's hit a minimum, turning around, any of that sort of terminology. And where it turns around is at, that's its location. So this is minus 1 centimeters from the origin. All right, so that's what's happening at time 2 seconds. And the last part here, so I've sort of put comments there. I'll leave that, fill it in later. At what time does the object reverse direction? Find the position of the object at these instances. At what time or times? So that's what we've basically just done. Here it's reversing. So it's reversing at time equal to 2 seconds. When, and the position is minus 1 centimeters. All right. Next part of this, E and F, draw a motion diagram for the object. So we can do that now. We're at 0. It started, if we go back to here, remember it started at plus 3. So our point starts 2, 1, minus 1. Here it is at 3. It starts there at time equal to 0. Then when did it go through? Do we get the origin? No, we've found out at 2 it's at time 2 it's turning around, but we didn't actually find it's at the origin. It's going to be at the origin at times 1 and 3. So it's here at time equal to 1 and 3, and it's here at time equal to 2. So equal sign. All right, so our point is starting here, going down through the origin, stop, turn around, and then come back. So that's where it's stopping at that point. All right. For what time intervals is the speed decreasing? Okay, so remember, it's going to be going at a certain speed, then it's going to slow down, stop, turn around, and go fast again. All right, so that's what you can imagine, even just from looking at that concave diagram to start with. If it's coming down, slow down, stop, getting faster. If you want some graphical way of looking at that, then here's our graph. That's our function, the initial function for t squared minus 4t plus 3. Our velocity we can put onto here. So there's our velocity. And remember, if we want the speed, you just want to take the absolute value. Let's pick a color here. We'll go red. Is your absolute value of your velocity function. So that means whatever's negative becomes positive. So it comes straight down here and then follows the positive, stays positive. So where is the speed decreasing? Where it's getting less. So it's decreasing between 0 and 2. In all that region here, the speed's getting less. Now the speed's getting more. So from 0 less than or equal to t, time less than or equal to 2. Make it equal to, as those are your endpoints of your interval. All right, so I'm going to leave it there. I've got another example here, number 6, that you can look through, but I think that's enough. It's a long video, but as I said, it's a really important area, and it's worth taking your time to really understand this, because you can pretty well guarantee getting a question on this in your final exams. Anyway, thanks for listening, IB, and hope you have a good evening. Bye for now.